So I'm going to change over the presenter to Eric, and he's going to go through the Abaqus updates.
Okay, thank you for your time. Okay, bye.
Okay, so good afternoon, everyone. I hope you can see my screen right now. Is the screen visible?
Looks good.
Quick review of the agenda on a brief introduction. A few words on the release schedule. The vast majority of this afternoon's presentation is going to cover Abaqus 2016. I'll mention a few words about the power of the portfolio and wrap it up with a summary and some questions. So with that, let's jump right into it. And what I'm showing here on the screen right now is the way that we within Simulia and DS view technology. And we like to view it on two dimensions. You can see here in the columns we have disciplines or multi-physics disciplines: structures, thermal, fluid, electrical, and so forth. Controls and whatever. Of course, Abaqus is very much focused on structures and thermal, and we've introduced fluids and electrical in recent years as well. Now in the rows we've got multi-scale, and here we go from the very bottom, micro scale, maybe non-continuum, and even with some recent acquisitions of DS, particularly Acceleration, even down to the molecular and atomic scale. And then we can go up to the physical scale. This products and parts, macro continuum scales. Again, this is where Abaqus is focused. And then we can even go to higher levels of abstraction, logical models, simplified representations, 0D, differential equations, and so forth. And then the highest level of the abstraction, functional, describing in terms of requirements and so forth. And again, this is a space that DS has products that span the whole range. But of course, today our focus is going to be on just a fairly small part of this, which is right here, which is where Abaqus lives. Right? Before getting into what's new with Abaqus, I want to share our friend, Mr. Confused. I'm sure many of you can relate to this. I know I certainly can. In years past, when you had to use multiple products to get your job done, it was, quite frankly, a nightmare sometimes to figure out which product worked with another product and manage different versions of files because they're incompatible with different releases, blah, blah, and so forth. Over the past few years, we've found ourselves in the position where, after acquiring these technologies, we can solve this problem. And that's exactly what David mentioned to you earlier, is that rather than having different products with different release numbers on different schedules that weren't compatible, we can move ourselves to a state where all of these products have aligned schedules that developed on a common development environment, and the data is compatible between these different versions of the programs. And we're rolling this out literally right now. As we mentioned, this new versioning scheme and all of these new products are available as of about a week ago. Okay, so let's talk about Abaqus. And I think the first area I want to focus in on is contact. I'm sure if I did a survey of everybody in attendance here today and asked you if you use contact in your models, that everybody's hand would go up. And if I asked you if you've had some challenges solving some of these contact problems that always seem to increase in complexity, I'm sure just about as many hands would go up. And this is something that we've recognized for a long time, and it was almost 5 years ago now that we introduced the concept of general contact into Abaquv Standard. And our vision for general contact is to remove all of those barriers that have existed that were related to numerical conditions and convergence and so forth, allow you to focus on solving the problem at hand, engineering, and have the software handle all the numerical details and make sure that we can get to a solution. So this is, of course, very challenging. I think we've made great strides in this area, especially if I think back 10 years ago or more and compare the problems that we solved then and the challenges we faced then compared to today. So I think great progress has been made in this area. So anyways, when we, before we had general contact, our contact was based on what we called node to surface. So we had slave nodes interacting with master surface facets, and that served us very well. And I'm sure many of you still use that, contact pair, node to surface in your work today. And that's fine. However, there were some inherent limitations to the node to surface formulation, and that's why when we first set out to implement general contact, we built it around a new type of formulation that we call surface to surface. So unlike the node to surface formulation, surface to surface enforces contact constraints literally facet by facet in an average sense, and that has some desirable properties. For example, it smooths out the solution and provides improved convergence. Also has accuracy benefits, more accurate contact pressure results, and also relieves some of the modeling burden with the node to surface formulation. The choice of master and slave surfaces and the underlying mesh resolution were much more important than they are with the surface to surface formulation. The surface-to-surface formulation, as I mentioned, forms the kind of the foundation of general contact, but there are many situations as solutions are involved in particular where surface-to-surface may change into edge-to-surface or edge-to-edge. And for this reason, and you can see some examples of how that might happen on the screen in front of you now. And so in order to account for these situations, we introduced what we called supplementary formulations, edge-to-surface and edge-to-edge. So that allows us to handle more general contact conditions and also expanded contact in Abaquv Standard so that it could handle beam-on-beam contact, which is something that was not possible except for very special cases of tube-in-tube elements in Abaquv Standard. So we have these three different formulations available in Abaquv Standard, and as solutions evolve, particularly with large deformations and large displacements, we can transition between these different types of formulations. So what started out as surface to surface can become edge to surface and sometimes even edge to edge. And achieving a converged solution requires very smoothly transitioning between these different formulations. And that's really what the enhancement on the screen here is in Abaqus 2016, is a significantly improved heuristics when we transition between these different contact formulations. So we've seen examples, practical production type models where the difference in convergence behavior is tens to even 2 orders of magnitude, fewer iterations, which for you maps to increased performance. So we're going to continue to enhance general contact, and we're hoping that many of you are using this as your default today, and we certainly want to hear from you if you are, and in particular, if you're finding problems that general contact struggles to solve. We'd like to hear about that so we can improve general contact. One example of where we've gone ahead and improved general contact further based on feedback is in Abaqus 2016, where we're now introducing a new fourth type of formulation, which we call vertex to surface, which can crop up in some certain situations as well. You can see examples here. This top-like structure is literally a vertex or a point in contact with a surface, and you can see here a beam end in contact with a surface or a corner of a feature edge of a shell. So we've introduced a new vertex to surface supplementary formulation that improves the contact behavior, i.e. convergence behavior in particular, when these types of situations arrive in models. So now we have 4 different types of formulations in general contact, and we believe that we've pretty much covered the bases at this point in time. Sticking with general contact, another enhancement that we've made based on customer feedback is related to the edge-to-surface formulation. What you're looking at the screen here is a beam element rendered as a cylinder that has a wedge-shaped shell structure being slid down on top of it. In the initial implementation of edge-to-surface, we only allowed a single contact along a segment of an edge at one time at the same place. and that resulted in a situation like you can see on the screen here to the left, where as we slide that shell structure onto the beam, you can see that there's penetrations on one side because we're only accounting for one contact at most. In the new release, Abaqus 2016, we've fixed this issue. We can now account for multiple contacts, at the same location along an edge, and you can see the results here on the right. Of course, accuracy is improved, but just as importantly, convergence behavior is also significantly improved. Output is among one of the most popular RFEs that we have in all of Abaqus. Each release we focus on implementing as many new output variables as possible, and this release is no different. One of the more popular requests we've had in recent years is expansion of contact output for Abaqus Explicit to include the so-called CDISP family of output variables, so contact opening and contact and slip in the local 1 and 2 directions. So those are available now in Abaqus Explicit, and we've also implemented a new member of this family called C-Slip EQ, so it tracks the total distance that a point on the surface has slipped relative to its opposing surface, along with output variables tangent directions, so it gives you the directions vectors as this slips along. So this enables certain types of wear calculations. That was the primary use case that we were targeting with this enhancement. Another output variable that's been very popular in Abaquv Standard, especially when it comes to diagnosing contact problems with C-status, whether a node is simply opened or closed or sticking. So that's also available now in Abaqus Explicit. A couple more contact-related enhancements I'd like to talk about. First is what we call linearized contact. So I'm sure many of you can relate to situations where you've built a model and it has these large flat surfaces that are coming in contact. For example, perhaps it's a bolted assembly such as shown on the screen here, and you've been very careful to position them perfectly, and everything is nice and touching in contact at the very start of the simulation. And we type Abaqus job equals, and the first thing that happens is 100 points open, and then 50 points closed, 200 points open, et cetera, and usually we're going to converge, and we're going to get back to where we started from, but it can take a lot of time, especially for large models. So what this enhancement does is it avoids those so-called what we call severe discontinuity iterations using a specialized solution technique built into the solver. It's only appropriate, though, when the model is otherwise linear. And that means the material behavior is linear, small sliding, small displacement, small deformation, which does cover a class of problems that are fairly important in practice. This enhancement is something of a research topic still. It's not quite ready for full production use. In particular, there's a lot of error checking and consistency checking that we need to do within the initialization phase to make sure that features that aren't supported by this capability creep in there. So it's for that reason that in this initial unveiling of linearized contact, it's available only from one of our 3D experience applications. We're working very hard right now to make this a little bit more robust, and you can expect to see this available in a very upcoming release of Abaqus. And we're also working to expand the scope of this to larger problems. It's currently limited to relatively small and medium-sized problems. This is primarily driven by the memory requirements that are needed within the solver. But you can see some examples here of the types of speed-ups that are possible for problems where this technique applies. The middle column is wall time SDI, the traditional contact method, and then the next column is wall time, this linearized behavior, and you can see speed up from 2 to almost 15x, which is quite significant. One last enhancement in the area of contact is what we're referring to as CAD-enhanced contact. So I'm sure some of you are familiar with the surface correction technique that we introduced for cylinders and sphere type geometries in recent releases. Basically, if you had cylinder and cylinder or sphere and sphere, and you gave us some parameters that analytically described the real geometry, we can include that information into the contact calculation. So the cartoon you see on the screen describes the technique schematically. Here you can see we have the real geometry. We discretize the real geometry, which introduces some differences between the mesh and the real, and you can see that shown by the arrows on the screen. So the essence of the technique is if we have information about the real geometry, we can compute the difference between the real and the mesh, shown as a correction factor here in the schematic, and include that in the contact calculations as a correction and get a more accurate result. And so, as I mentioned before, previous releases, we've had this available for cylinders and spheres, and you can specify those with just a few numbers in an input file or a check button in CAE. In this release, we're extending that concept, and again, this is also something of a research topic still, but we're extending this idea to include these corrections from the underlying CAD representation. And you can see some of the results that are possible with this example on the screen here. It's a doubly curved surface, something that you might expect to see in a production type part. On the left, we have the contact pressure results based on just a mesh without any corrections. And then on the right, you can see the pressure results are uniform, as would expect for this loading case where we're just compressing it with the corrections applied. Of course, in order to compute these corrections, we need an underlying CAD representation, and it was only natural for us to base that off the CGM geometry kernel. So that's what we've done initially, is derive these corrections from the underlying CAD geometry based on CGM, which is the kernel of CATIA. So this is also initially available from select 3D experience applications. Of course, if we can take other CAD formats and convert them into CGM format, which there are many translators available that can do that, then we can apply this to more general other types of CAD geometries, other formats, and so forth. So this is, as I mentioned, still something work in progress, giving you an idea of what we're working on, and you expect to see this enhanced and made more widely available going forward. All right, so that's it for contact. That's one of the big areas, of course, in mechanics. And then, without elements, I guess we'd have nothing. So it's not much of a surprise that with each release we expand our element library. One of the enhancements in this release is a new pyramid element for stress analysis. So this is intended for, the primary use case is hex-dominant meshes. We like hex meshes because they're more computationally efficient. In particular, you can get the same with fewer elements, but there's some cases where you can't mesh the whole thing with hex elements. You need to fill a few tets in, and this element allows us to transition between those hex and tet elements. It's a very popular RFE, especially from customers who want to do hex-dominant meshing and squeeze a few tets in there. This is available in Abaquv Standard in Abaqus 2016, and we are working literally as I speak to add this element into Abaqus Explicit as well. Some additional elements that were added are what I'm referring to here as multi-physics elements, and there's a whole bunch of them. I think almost 20-something elements added for coupled temperature displacement, coupled pore pressure displacement, and the three-field pore pressure temperature displacement procedures. Basically, what we've done here is add some elements that work better with contact, fill in gaps, wedges, and so forth. So different types of element topologies and formulations to fill out this element library. And another, I think, it's a quite interesting element or 3 of them, I should say, introduced what we refer to as surface stress elements. And the idea here is to provide more accurate, or provide the most accurate results on the surface where they're oftentimes needed. For example, in fatigue calculations, which quite often rely on results on the surface. Of course, with most of the traditional element types, stress is calculated at the integration points and strain, and those are inside the element. In order to get results at the surface, we have to extrapolate, which sometimes is, or in many cases for that matter, perfectly adequate. But if we have coarse meshes or other types of situations where that extrapolation can lead to erroneous results, for example, this beam here, this is kind of a contrived example to show just how bad it can go. On the right, we have the real solution, and if we extrapolate in this case, then it looks as though the beam had completely yielded. So what we've done with these new elements is move the integration point. So the integration points where the stress is calculated is now coincident with the nodes, and there's also some other integration points, interior and mid-side and so forth. So the net effect is that the most accurate stress calculation is available where you need it on the surface. And we've got 3 elements that use this new formulation. You can see them here: a linear brick, a hybrid version of that for incompressible materials, and a second-order TET version of that as well. So I mentioned that the C3D10HS is actually an element that was available in the previous release, and you might have noticed this or heard us talk about that. We were calling it C3D10I in the previous release, so we've changed the name of that element to C3D10HS to be consistent with these other elements that we've introduced. As I mentioned, there are a few more integrations associated with these elements. So, at the element level, they're a little bit more expensive. However, when rolled into a large model, and particularly models where the solver cost dominates, which is typically the case, the added cost at the element level is fairly insignificant in the overall solution. And last element that I'd like to talk about is I think something quite different for Abaqus, which is a fluid element. So this is a 1D truss-like element for pipe flow. And we also have a connector element flavor of this. So completely no structural degrees of freedom here whatsoever. We're just looking at fluid flow through pipe elements. So you can analyze piping networks. It's based on Bernoulli's equation and carries all the assumptions that are behind Bernoulli's equation. Various different load types: pressure, flow rate, gravity. And we can also model losses arising from friction and transitions between different types of joints. And you can see a picture here at the bottom, the different types of joints that we can model using like loss factors. One of the unique capabilities of this element is the ability to couple with 3D pore pressure elements, and we do that using a special tie constraint. You can see an example here on the bottom right-hand side of the screen where an application of this. This is from the oil and gas industry, and in fact these elements were implemented through a partnership that we have with one of our large customers in that industry. In this example, we're injecting fluid through the pipes. You can see the vertical line here. So we're injecting fluid through the pipe, and then using the tie constraint, that fluid is then pumped into a pore pressure domain, soil, and results in stresses within that soil. So this was developed for a very specific application. Of course, the pipe elements are very general for piping analysis, and I'm sure that some of you will find unique uses for this tie capability, and would love to hear about them if you do. Another very popular RFE was how we handle ties between bodies meshed with solid elements. So I'm sure many of you are familiar with the requirement up until now that when you tie 2 bodies meshed with solid elements together, that we needed to adjust the surfaces such that they were precisely in contact at the start of the analysis. And if we didn't do that, we could get some erroneous results because that offset is not taking into account, mainly because these elements don't have rotational degrees of freedom at those nodes. So, our thinking all along has been that if you have gaps like this in between solid mesh parts, that it can oftentimes represent a modeling error. Either the parts weren't positioned correctly, or the mesh was not adequate enough to resolve the geometry. But based on feedback from all of you, we've realized that there are many situations where you realize that the modeling is approximate, but you're not really concerned about the results in that area, and you'd like us to just tie these things together and handle the fact that they're not precisely touching. That's exactly what we've done in Abaqus 2016. Is we've implemented a technique where we can properly handle those offsets in the face of rigid body rotations. So you can see here that in Abaqus 614, we get an erroneous result, and if we put stresses on there, you'd see a very high stress concentration, whereas in Abaqus 2016, those rigid body rotations are handled correctly, even if we don't adjust. So this is an Abaqus Standard. A similar capability is also implemented in Abaqus Explicit, although it's within the framework of surface-based cohesive behavior instead of the star tie capability. And this was primarily due to significant differences in the way constraints are formulated between these two solvers. In the future, we'd hope to unify the user interface, but that's work for the future. Material modeling, of course, we got contact, we got elements, so we also have to have materials. Quickly mention a few enhancements here. Addition of rate dependence to the kinematic hardening plasticity model, so this is typically used for cyclic loading and so forth. A number of new materials in the area of geomechanics, one of which was the extension of clay plasticity to orthotropic behavior, and import between standard and explicit of the Johnson-Cook plasticity material models. This is commonly used for high rate deformation problems, typically impact and so forth. All right, so now I'm going to switch gears and spend a few minutes talking about performance, which is another very, very important topic for us. In past years, we've talked about performance in terms of parallel processing using MPI and clusters, domain decomposition in Abaqus Explicit. A little bit more recently, our foray into using GPUs to accelerate the direct sparse solver in Abaqus Standard. And we've seen some fairly good results, particularly for large models there. Speed ups 2 to 5 and sometimes more by leveraging GPUs for the direct sparse solver. So in this release, we're continuing to work to find ways to leverage GPUs, and one area we've done that is the AMS eigensolver. So as a reminder, the AMS eigensolver is an approximate technique for extracting eigenmodes or many eigenmodes from very large models. It's been available in Abaqus for almost 10 years now, I think, since our first implementation. In this release, we've extended the use of GPU to certain phases of the AMS solver, and you can see it right here. We're calling it the AMS solver. I'm not going to go into all the details of what this chart shows, because I think the most important number for you is how much did it speed it up overall, not how much did different phases speed up. So for this particular example, 13.7 million degrees of freedom, 5,000 modes on a 20-core machine. You can see a speed up here of about 27%, which is pretty significant. Another area where we've leveraged GPUs now is the steady-state dynamics procedure. So again, as a reminder, this is a procedure where we apply harmonic loads over a range of frequencies and compute the peak response. 2 releases ago, we implemented parallel processing for the steady-state dynamics procedure, and you can see the chart here showing the progression from 613 to 614, 2016. As we increase the number of cores, you can see that we get speed ups as would expect by using more cores, and you can also see from release to release speed ups here as well. But what is, I think, most amazing here is that now when we throw a GPU at this problem, the speed up is just enormous. For example, if we look and focus right here in this column, one core with one GPU, it takes 566 seconds to solve this problem compared to almost 7,000 seconds if we're going to solve this problem on one core without a GPU. So essentially, I guess we probably shouldn't even have bothered implementing parallel processing and just implemented GPUs right from the get-go. So I think this is a great example, the best one we've seen so far of the benefits of GPU, and this is primarily because the steady-state dynamic procedure, lends itself quite nicely to GPU acceleration because it's essentially just a bunch of vector-vector multiplications. So it was particularly straightforward to implement this. Okay, so in the last few minutes, I'd like to talk a little bit about some enhancements to Explicit. The coupled Eulerian-Lagrangian technique has been available for many years. It was really targeted towards large deformation, high rate problems where traditional Lagrangian meshes would become entangled and we couldn't keep running on the machine. So by using an Eulerian technique, the mesh stays fixed and the material flows through the mesh and we avoid those problems. And it's coupled because we can couple the Eulerian material surface with Lagrangian bodies through contact, which allows us to do things like shown on the screen here, fluid structure interaction, for example, and so forth. One of the limitations of the Eulerian technique, though, is that it's difficult to follow the results at a specific material point. With traditional Lagrangian elements, the elements move with the material. Here in the Eulerian technique, the material flows through the element, and in order to follow a material point, we need to have tracer particles, and that's the enhancement here. It's been a very popular request, and it's available now in Abaqus 2016. The animation you're showing on the screen is a type of sloshing analysis. You can see we have a shell mesh representing the tank. This is a cross-section through that. And what you're looking at inside the tank is tracer particles with the Eulerian mesh removed. So this is not a particle method. This is actually Eulerian elements in here. And what you're looking at here is the material points as they move through the Eulerian mesh. The table here is showing that when we insert these tracer particles into the mesh, the performance impact is fairly negligible. Sticking with Explicit, another technique that we've introduced recently, I think just last year actually, is the discrete element method. So this is truly a particle method where particles interact with each other via contact. Typical applications for this are processes, manufacturing processes, process simulations. You can see an example here on the screen where we're sorting some sort of an aggregate based on the size. This could be products on an assembly line. We've had some customers look at modeling soil with the DEM approach, granular soils, and trying to model them using particles interacting with each other. It was initially released last year, or 2 years ago, 2 years ago, and we're continuing to enhance that. One of the biggest enhancements and one of the biggest limits to the usability of this technique up till now was the ability to introduce particles into the domain. And we've addressed that in a fairly big way in this release. Very, very general techniques for introducing these DEM particles into the domain. You can see some examples on the screen here. An inlet that's expanding, an inlet that's rotating, moving. You can specify size distributions using statistical functions. The mass flow rate and inlet velocity can be user-defined and so forth. So very general capabilities for introducing particles into your domain. And another enhancement to DEM was introduction of an adhesive-based contact. Our initial implementation was restricted to Hertz normal contact. Now we can also model contact where the particles are adhering to each other. And you can see the example here on the screen. This is a mixing operation inside of a tumbler. and very different behaviors depending on whether the Hertz contact or adhesive contact is used. Sticking with the particle method theme, another area of improvement was in the SPH, or smooth particle hydrodynamics capability. So this has been available in Explicit with several releases now. Unlike DM, which is truly discrete particles interacting with each other, SPH is a continuum method, and where the particles interact with their neighbors through a kernel function, and we're showing that schematically on the screen here. So the particle at the center, the strain there, is computed by looking at the motion of neighboring particles. So this does lead to some anomalies, particularly when we have particles interacting with a boundary. And you can see an example of this in the animation at the top of the screen where the particles are interacting with this boundary through contact. The behavior is exhibiting some non-physical characteristics. And the reason for this is because the particles at the boundary don't have any neighbors on the other side of the boundary that they're interacting with through these kernel functions. So our solution to this problem is shown with the cartoon in the middle. We introduce these so-called virtual particles on the other side of the wall that allows us to compute the fields more accurately, and the net result is a much more physically realistic behavior when modeling these types of scenarios. And I think the last enhancement I wanted to mention here today, also related to SPH, was what we call uniform grid particle generation. Not many pre-processing tools can generate particles directly, and the approach that we've taken in Abaqus was to essentially mesh your geometry as you normally would with traditional Lagrangian type elements, and then we can convert those elements into particles based on user-specified criteria. Oftentimes convert at time zero, which basically just gives you a particle mesh generator. But in some situations, you may want to rely on the traditional Lagrangian elements until some extreme event occurs where maybe the elements will fail, and then we can convert the particles on the fly. The initial implementation, the particles were generated based on the underlying mesh. If those elements had large aspect ratios or were very distorted or so forth, that would influence the particle generation. In this release, we've introduced what we call the uniform grid method. So no matter what the topology of the parent elements are, we superimpose the uniform grid and use that grid to generate the particles. You can see the image here on the screen, a much more uniform distribution of particles, which leads to increased robustness and accuracy. So that's what I had for Abaqus. So just moving towards the conclusion here, a few words on the power of the portfolio. I hope many of you have heard of this, and I know many of you have adopted this. So just briefly, the concept. Of course, Abaqus has been around since 1978 and is really the flagship technology of Simulia. In recent years, we've acquired other technologies, iSight, Tosca, FE-Safe. We talked earlier, Tosca for process automation and parametric optimization. Tosca provides topology and shape optimization. Of course, FE-Safe, we heard about that a few moments ago for durability and fatigue life calculations. We've aligned the schedules. Of course, it also makes sense to simplify the process of getting these tools into our users' hands. That's what we call extended packaging. So with a single type of license, enables the interactive seats of CAE, iSight, and FE-Safe. A single type of token, we call them extended tokens, enables compute for Abaqus, iSight, Tosca, and Fatigue. So simple to use, puts all the tools available to you in one clean little package. So with that, let's wrap this up. As you can see, the technology train here at Simulia just keeps rolling on. I really only scratched the surface. If you refer to the release notes, you'll see many other enhancements that are available in this release of Abaqus. It's available to you now. We're very excited about this release, and we look forward to hearing about your success. So with that, we will conclude, and I think we have a few minutes left for some questions. Huge numbers of questions. All right, so let's try to get through these. So is general contact available for 2D or just 3D? And the answer to that is it's only available for 3D right now. Not surprisingly, 2D is very popular, and it's something that we're giving serious consideration to for a future release. How are the transfers between surface to surface and edge to surface handled? User intervention required? I think that was the essence of the question, and the answer to that is no. All of this is internal. We mention it just to give you an idea of how much work we're putting into this, but again, our goal is for all of these algorithmic details to be done behind the scenes. You focus on solving your problem. We'll focus on getting a converged solution. Is C3D8S based on C3D8 or C3D8I? So it's a different element. I mean, it's similar. I mean, kinematically, they're basically identical. They've got 8 nodes, and the kinematic calculation is the integration points that are relocated. So similar kinematically, but the integration is different. Has the Abaqus CA mesher been updated to use the new pyramid element? And the answer to that is no at this point in time. Let's see what else we can give here. DEM, is it restricted to spherical particles? Can you use composite particles, that is a combination of spheres? So today it's spherical, but we are looking at introducing different shapes, if you will, for DEM. Okay, so here's one. What bugs have been fixed? So in Abaqus 2016, so many, and I'd refer you to your local account team if there's something specific that was affecting your work and you want to know if that has been fixed. So now that we have surface stress elements, can we avoid using membrane skin elements? And I would say the answer to that is absolutely yes. That was really one of the use cases that we were trying to address. Also mention that I think a little known feature that sometimes comes up is related to stress on surfaces. We introduced the capability several releases ago to limit your output to just the surface. So if you have very large models, sometimes the ODBs could be big. So you can get results on just the surface as well. I'd mention out there. Another question here related to GPUs. How many can be used per analysis or core DMP SMP setup? So how many can be used and how many actually make a difference can be different questions actually. In general, we find that for a single compute node that has the number of cores that typically exist today, 2 GPUs per compute node is typically optimum, particularly for the larger models. Of course, for smaller models, the GPU benefit is less, but for large models where you're running in DMP parallel, we find that 2 GPUs per node is typically, gives the best return. So can the slides be distributed with the webinar? So I do believe these are going to be available on the Simulia Learning community. Maybe Katie can confirm that. One other question here. Why 2016 SMP is slower than 614 when using 8 or 16 GPUs? So I'm not sure what we're referring to here. I hope it wasn't on one of the slides. I don't think it was. Typically not the case. Okay, so it is. He's looking at the steady state dynamics case where you can see a small difference in performance. So that can happen. I don't know exactly why that happens in this particular case. Oftentimes it's related to improving the algorithms to increase robustness. It's sort of conservation of correctness, I guess. So I don't know exactly what's going on in that case. So it looks like we're getting short on time. So I'd like to thank everybody for showing up. And again, we'd love to hear from you and what you're doing with Abaqus. So that's it. Thank you.
Thank you, everybody. Thanks, Eric.